Good afternoon, everyone. So, in the previous class, I was discussing about the reagents in organic synthesis. So, I am the TA of this course, which is instructed by Professor Subhash Chandra Pan. So, during these classes, I will try to solve some questions based on this topic. So, the questions are taken from the previous year NET GATE and also some important books. So it will give you an idea or broader perspective about this chapter, and which will help to solve your assignments and other questions also. So let's start. So in the previous class I discussed about the oxidation of alcohols. So there are three types of oxidation is possible. While like the alcohol is 1 degree, then it will be oxidized to aldehyde. If the alcohol is secondary, then it will be oxidized to ketone, and if it is tertiary, there will be no oxidation. And if it is alcohol and you apply some strong oxidant or oxidizing agent, it will directly oxidize to acid. That is, it's going through it via two-step oxidation. Like it will oxidize to aldehyde, and aldehyde will again oxidize to acid if you are using some strong oxidizing agent. So there are two types of oxidizing agents, like some are transition metal containing and some the other reagent. Other reagents means the reagents which doesn't contain any transition metal. So they are divided into two types. In the last class we discussed about the transition metal containing reagents. Today I will discuss about those other important reagents. Initially when this oxidation topic introduced to us, scientists usually used those reagents containing the transition metals. But day by day we know the transition metals are not that much environmental friendly, so we try to substitute those transition metal containing reagents by some reagents which doesn't contain any transition metal, that will be more environmentally friendly, that is greener, because we always try to approach our procedure through a greener approach, so that if you can eliminate the use of transition metal, or if we can reduce the use of transition metal, that will help us to in a good way affect our or some improvement for our environment. A very useful group of oxidant for oxidation for alcohol to ketone, which contains no metal, is DMSO. DMSO usually, you have seen DMSO using as a solvent. So DMSO can be used as a reagents also. So if we use DMSO along with one of the electrophilic agents like DCC, acetic anhydride, trifluoroacetic anhydride, oxalyl chloride, or sulfur trioxide, this type of oxidant if we use along with DMSO, that combinedly that can act as an oxidant to oxidize alcohol to carbonyl compound. If we are taking 1 degree, then it will be aldehyde, 2 degree will be ketone. So if you take this reagent, it can be also used as a oxidant. So here I have shown one of the example. Here they use DMSO and dicyclohexyl carbamide. This is the full form of DCC, dicyclohexyl carbamide. Dicyclohexyl carbamide. If we use this DMSO and DCC, it will oxidize the alcohol to aldehyde. Now you have to find the alcohols. There is a alcohol group, as this is a 1 degree, so it will be oxidized to aldehyde. Mechanism we will discuss after this. There is another type of reagent. I said if we use acetic anhydride also, so if we use DMSO along with acetic anhydride, this will also can act as a oxidant for oxidation of alcohol to aldehyde. This is also 1 degree, so it will be aldehyde. Okay. So if we look into the mechanism of DMSO DCC, this is called DCC, dicyclohexyl. In case of DCC, these R groups are cyclohexyl. Like these R groups are this cyclohexyl group. These R groups are cyclohexyl group. These R groups are the cyclohexyl group. Now, if you are adding DMSO in it, this DMSO structure is DMSO, dimethyl sulfoxide. This can stay as in this way also, like oxygen is taking the lone pair, so the sulfur will be positively charged and oxygen will be negative. So yeah, as a whole it will be neutral. As a whole it will be neutral. You may think then okay, the charge space, how can charge space stay? But as a whole this is neutral. So this can stay as in this way also. So this O minus will attack to this carbon center and this will open and it will take up a proton from anywhere in your substrate or somewhere. After that, if you are adding an alcohol, this oxygen lone pair will attack to the sulfur and form this intermediate. Now, as there should be at least one hydrogen on this alcohol, there should be at least one hydrogen on this alcohol. So this hydrogen is there, this hydrogen is this one, this comes at this place and we get, sorry. So this DMSO has one proton, so one proton from this DMSO methyl will be removed and this will take off, like this is the CH3. This one proton is this one. Okay. So one proton will be removed, then this goes here and this removes from the system. After that, this becomes a negatively charged, so this will take up this proton from this alcohol and goes here and this gets removed. So we are getting ketone as our product from alcohol, and as a byproduct we are getting dimethyl sulfide and amide. Okay, so the byproduct is amide. Is we know that if we amide can be water soluble also, so we can easily remove that from the system by use, as it is water soluble. So if you want, some of you know about workup and all, so if the byproduct is water soluble and if you perform the workup process, so what will be the organic solvent will take our product, that is the ketone, and the byproduct, which is water soluble part, will go to the water content, and when you remove the water part, it will go along with the water part. So these are the byproduct. These are the byproduct. these are the byproduct. So this will be removed from the system easily. There is no such transition metal is there. So there is another example. If you use any electrophile instead of DCC, if you use any electrophile like acetic anhydride or trifluoroacetic anhydride, what will happen? If you use any other electrophile like this way, then what will happen? This O minus will attack to this electrophile. After that, when the alcohol is added to this species will generate. After that, when the alcohol is added, this alcohol which oxygen will attack to the sulfur center. Then the after process is same like the previous one. There will be one so this will come here and this gets removed from the system. So this species will generate. After that, when we this after that this proton is taken up by this CH3 minus like the previous one, and this comes here and this gets removed from the system. So in this case also we are getting ketone. Okay. Now as an electrophile, if we use oxalyl chloride, that type of oxidation is specifically called Swan oxidation. Right now it is highly used in laboratories, which is called Swan oxidation, because of its high reactivity, as well as there is no use of metal or any toxic reagent, because whenever we are using oxalyl chloride, the byproduct is carbon dioxide, which is also a favorable thing. Oxalyl chloride is this one. If you know about oxalic acid, in oxalic acid, just replace 2 hydrogen with this is called oxalyl chloride. So this oxalyl chloride will remove, then we use, and this is called Swan oxidation. So let's solve some examples. Now whenever you see this type of compound and it added DMSO, P2O5 and ET3N. Now we know P2O5 can also act as an oxidant. P2O5 can also act as an oxidant. Electrophile. P2O5 can also act as an electrophile because phosphorus has a vacant d orbital, so it can also act as a electrophile. So we know DMSO along with some electrophile is act as a oxidizing agent for alcohol. So we have to see that if there is any alcohol is there. Yes, there is alcohol. And in DMSO oxidation, it will only oxidize the alcohol. It will not oxidize our double bond. There will be no such epoxidation or dihydrosilation which we discussed in the earlier. So it will just oxidize the alcohol. It will just oxidize the alcohol. This part will be, the other part will be unaffected. So the product will be this one. Only this alcohol will be oxidized to ketone. Next is this one. This is also same. If we use this oxalyl chloride along with DMSO. So I have drawn a mistake. There will be COC. So if you use DMSO with oxalyl chloride, what will happen? It will is a Swan oxidation. This is a Swan oxidation, and this Swan oxidation will lead to oxidation of this alcohol. So the other part will be same, just it will be CH. I am not drawing the other part. The other part will be same. This part will be just CH. Okay. All these these questions are taken from books, so it may come to your next examination. So if you want to, you can note it down. In exams, actually, they will not ask directly this time. They will add some, like they will add some two reactions in a one. Like if you are like they are adding after this product formation, they are leaving this is reagent 1, and after that they are giving reagent another reagent as 2, and they are giving H plus. Suppose they are giving H plus, what will happen? Just after this one they are giving H plus, what will happen? If the H plus is given, obviously this H star part will be hydrolyzed. So this part will be, this ketone part will be unaffected. So it will lead to this as a product. So like this way, they will not stop at a one step. They will give another reagent and will ask what will happen after that. You have, so if you know that okay, the first DMSO-P2O5 doing this reaction, so the H plus one is everyone knows, like if you are adding H plus in ester, it will undergo hydrolysis. That part is everyone knows. You have to know the first part. Next is this one. Now they are given DMSO and sulfur trioxide. I said sulfur trioxide can be also used as an oxidant. Now they are using DMSO and sulfur trioxide. Now there are two alcohols entered. This one and this one. Now can you say which alcohol will be oxidized? Both of them will not. For just an idea, like both of them will not get oxidized. One of them will be oxidized. Which one? Obviously,
second down one.
yes, obviously this one, because this is tertiary. This is a tertiary. This is a tertiary alcohol. So we know that tertiary alcohol will not get oxidized because there is no proton. There is no such proton available here to be removed. In your mechanism you have seen you have at least one proton here to get removed and to carry forward this last step of the oxidation. So you have to have one proton. But in case of 3 degree there is no such proton, but if this is 2 degree, so there is a proton available here. So this part will be oxidized and will give us this as our product. Now suppose they are in the next step they are adding MCPB. You know this product. Now that the next step they are giving MCPB. What will happen? We have discussed this in the last.
Double bond will shift and form ketone.
No, actually MCPBA leads to the epoxidation of this double bond. MCPBA will lead to this epoxide of this double bond. another type of useful oxidant for the oxidation of alcohol to ketone that involves a hypervalent iodine. It's also called Desmartin oxidation. This oxidation undergoes a rapid oxidation of primary and secondary alcohol. Now if you have, suppose you in a reaction medium, you already have both the primary and secondary alcohol. Which will react fast between primary and secondary? Obviously the primary one. If you have both the alcohol in a reaction medium, 1 degree will react faster than the secondary. So this is the mechanism for this Desmartin reaction. This is a hypervalent iodine because this is in a high oxidation state and oxidation number. So this is +5. So if you are adding alcohol, this attacks to this iodine center and one of this acetate will get removed. After that, as at least one proton is required. So this one proton will be taken up and this goes here and this opens up and we get this as our byproduct and ketone will be generated in the reaction medium. So for this one also we need at least one hydrogen in the alcohol center. So if we try to solve these questions, so they have given this one. Now you have to add Desmartin reaction. So from Desmartin reaction, you know that there will be oxidation reaction and oxidation of alcohol. Now there are two alcohol centers, this one and this one. So this one is primary and this one is secondary. So which will react? If you are using this, suppose whenever if it is not mentioned as excess, if it is not mentioned that the Desmartin has been added in excess, in a bracket, if it is not mentioned in excess, you will always consider that one equivalent has been added. One equivalent has been added. One equivalent means with respect to the substrate, one equivalent has been added. So only one molecule will react. Only one center, which is not, the reagent is not in excess. So one molecule will react with one molecule of the reagent. So for this one, which one will react? This 1 degree. So if you keep the other part same, only this part will be oxidized to alcohol and other part will be same. There's another thing also, this is a protecting group. This is a silyl protecting group. By using this reagent also, this protecting group is also unaffected. It is not get opened up. This protecting group, we will discuss it in the upcoming classes. This is called silyl protecting group. This protecting group is also unaffected by the reagent. Now if we use this type of group, so this is a alcohol, but this is a conjugated with a triple bond. This type of alcohol can be also oxidized by using Desmartin. And as I said, Desmartin is only able to oxidize the alcohol. This triple bond will be fully unaffected during the course of the reaction. Okay. Next is this one. Here also this part is the alcohol part. So other part will be unaffected. Only this will be the ketone. I am not drawing the other part. It will be totally same as this product. Only this part will be the ketone. Okay. So the another type of oxidant can be used, which is tempo. So this is tempo, tetramethyl this this is tempo. Now if we add alcohol in tempo, what will happen? This oxygen OH will attack to this nitrogen center and this will open up. And for this one also you need at least one hydrogen. So this comes here, and the after mechanism is always similar to in all these cases. If you know why this alcohol OH will attack once, after that the mechanism is almost similar in every cases. So then this will get removed and we get ketone as our product, and this reduced tempo is formed. Now as tempo is bit costly, and if you are using, as after the reaction is tempo is getting reduced, so you have to use a excess amount of tempo for reaction. As just one molecule of reaction, tempo is gone. For one molecule reaction, the tempo is gone. So if you are using suppose 1 mole of substrate, for that you need at least 1 mole of tempo to oxidize it. At least 1 mole of tempo. That is huge for industrial purpose. So that's why, to reduce the use of the tempo, if we can use different type of hypochlorite or in chlorosuccinamide, that will use as an oxidant and it will regenerate tempo from its reduced form. It will regenerate tempo from its reduced form by using NCS or any hypochlorite reagent. If you use this type of chloride reagent, it will oxidize this reduced in medium. It will oxidize it and regenerate this tempo, and this tempo will again react with another molecule. So in that case, you can use tempo in a catalytic amount. This is similar to osmium tetroxide as we discussed last week. That if by this process you can use tempo in a catalytic amount. Like you can use 20 mole% of tempo, and if you use one equivalent of NCS, then the full reaction will be completed. But without NCS, you need at least one equivalent of tempo. That is huge for a industrial purpose. Like in this way, if you are regenerating your reagent in this reaction medium, it reacts as a catalyst. So this is another one of the example here. This is all a similar type of, as there is alcohol group. If you are just draw it in an open system like this. There is an alcohol and a ether center, so the alcohol part will be oxidized. So this will be okay. Similar in this case also. So as the tempo is reacting only on the alcohol center, this will not affect this carbon center. So the stereochemistry of the aldehyde will be same as the alcohol. This is not like that the aldehyde is attacking from this carbon. This carbon center is not taking part in this reaction. This is because you know all the reaction is happening on this carbon. Reaction is happening on this carbon because this oxygen will attack to this nitrogen. After that, proton will be removed from here, then this goes here. So this carbon is totally unaffected under the reaction condition. So the stereochemistry will be same from alcohol to aldehyde. Okay. You have to know that if the chiral center or if the stereogenic center is not taking part in the reaction medium, that stereochemistry will not be affected by the reaction. That stereochemistry will be unaffected. So here the carbon center is not getting affected by the reaction because it is not taking part in the reaction. This is totally unaffected. Okay. So let's solve some previous year questions. This I have tried to combine the questions based on whatever we discussed in the last class and today's class. So there will be the combined one. And after that we will discuss some new topic also. So which one of these following statement is true for the following transformation? So you have to get both the product. So one is, they are given this compound and they have performed a epoxidation of this alpha beta unsaturated double bond. They have performed a epoxidation of this alpha beta unsaturated double bond and they have shown both the product. One is above the plane, one is below the plane. Now they have asked which of the following statement is true. So from as it is going, as the reaction is epoxidation of alpha beta unsaturated double bond. So in the last class I have already told, whenever there is epoxidation of alpha beta unsaturated double bond, that is electron deficient double bond, the reagent will be hydrogen peroxide. And if the epoxidation is for electron rich double bond, electronically rich double bond, which has some electron donating group around it, that epoxidation will be performed by MCPBA. So as it is the epoxidation of alpha beta unsaturated double bond, so the reagents will be hydrogen peroxide. So these two options are already cut from our choice. So these two options are already cut from our choice because MCPBA will not be there. If we were adding MCPBA, which double bond would react? This one. If we are adding MCPBA, this double bond would react. But in our case, in their case, they had alpha beta unsaturated double bond undergoes this epoxidation. Now among these two, in one they have said B will be the major product and another one they have said A will be the major product. So which will be the major product? We know that MCPB reactions can, the epoxidation reactions going through this epoxidation reaction, this hydrogen peroxide. So this, as due to presence of this OH group, this can able to form hydrogen bonding. Now if there is a probability of hydrogen bonding, it will form a hydrogen bonding. Now you have to see, is there any probability of hydrogen bonding? No, because there is no such group in our substrate which can perform any hydrogen bonding, no OH, nothing. So, but there is this alkyl group which is below the plane. Alkyl group always give a steric effect. Alkyl group always give a steric effect. So it will give a steric effect. So if this group is below the plane, epoxide will form above the plane because it is giving a steric effect. So the major product will be option this A. So the correct option is option B. Okay. So here, as there is no such group leads to hydrogen bonding, this alkyl group only gives the steric effect. So that's why the option D will be the correct one. Let's go to this one. So there is a three-step process here from going there is three reagents, three group of reagents are given in all the options, three group of reagent. Now you have to form this product from this substrate. What will be the procedure to form for going this to this? I just give 1 minute, just think. All these reagents have been discussed in the last class, I hope. All this reagent, all this oxidation reagent, Jones reagent, PCC, MnO2, all has been discussed in the last class. And this is a protecting reagent. You know about this. If you write this way, this part, this looks like this. This is the aldehyde protecting reagent. And PTAC is just a catalyst, it will give H+. This is the aldehyde protecting reagent. all this reagent list MnO2 PCC has been discussed. So just give 1 minute, I will. Okay. So let's start. As it is a allylic alcohol, this is a allyl group benzene or a benzylic alcohol. This is a benzylic alcohol. So benzylic alcohol can be oxidized by MnO2. Benzylic alcohol can be oxidized. From this place you can see this is, if in this case this is 2 degree, this is 1 degree. Now instead of the concept of benzylic alcohol, if you add any other oxidizing agent, which alcohol will be oxidized first? Obviously this one. 1 degree is always preferable over 2 degree. So instead of this benzylic thing, if you add any other oxidizing agent, this 1 degree alcohol will be oxidized first. So this will be aldehyde first and this will be alcohol. So it will be harder to get oxidized after that and you get this one. So first we will try to oxidize this part. So if you add MnO2, in this one, what will happen? It will oxidize this benzylic alcohol selectively and the other part will be there. Now if you add a protecting reagent, this one, if you add this protecting reagent, it will selectively react with the aldehyde. Now why we are not oxidizing this one? If you would oxidize this part and add the protecting reagent, what would happen? It would protect at this place. Then that is not our desired product, okay? So that's why we are oxidizing first this secondary alcohol and then we are protecting it with the protecting reagent. Now if you add any oxidizing agent, like if you add PCC here, we will get this as our product. We will get this as our product. So which option we are going through? Option A. Okay, understood? So this is the way they will combine 2-3 reactions in a react and give you a question. Let's move to the next one. So what will be the major product in the following reaction sequence? MCPB is given. So you know what is done by MCPB? We know that benzene ring is very hard to react because it's due to its high aromaticity. This double bond is not that much susceptible for reactivity. So which will react? This double bond. This will be epoxide, undergoes epoxidation. After that, they have added this Lewis acid. This is the Lewis acid. If you add this Lewis acid, what will happen? This oxygen will combine with this Lewis acid. into this Lewis acid. After, so this will be a positive and a negative. So then to gain aromaticity, and this is a benzylic proton also. This is a benzylic proton also. So this comes here. Sorry. Okay, if you just so benzylic carbocation is stable. So if you just open up from this place, it will give this carbocation. Okay. Now as there is a proton available here, this goes here. And form this enol type of system. Now we know enolic double bond are highly prone to resonance, so this will come here. This goes here. So it will be, what will be our product? So option D. Understood? Option D. So like this way they will just combine a second step and try to make the question a bit complicated. Okay. Let's go to the next one. So the major compound X formed in the following reaction exhibited a strong absorption at mu max, which is 1765 centimeter inverse in the IR spectrum, and the structure X is. So there will be a product and which shows IR at 1765. That shows a IR at 1765. So what will be the structure of this one? So from this value 1765, if you know about IR, I don't know, from IR this value comes for a ester. 1765 usually a value of ester. 1765 is a value of ester. Whenever you get a value around this 1765, that means that compound contain a ester group. The compound contains a ester group. So in this four option, which one is containing ester group? This one. So from this one you can get an idea. Okay, this will be a product. Now if you want to know what is the mechanism, let's go to the mechanism. From this IR value you can get that okay, this compound contains a ester compound, and so this will be our product. So if you want to see the mechanism, so as there is a primary alcohol and you are adding PCC, what will happen? It will be oxidized to aldehyde. this will be oxidized to aldehyde. After that, as PCC is bit acidic, so it will get a H plus from the medium. PCC is bit acidic, so it will get H plus from the reaction medium itself. So it comes here and this open up. This will form an alcohol. This will form an alcohol. Now, as the reagent is still in the medium, so this alcohol center again get oxidized. This alcohol center again get oxidized, and we will get this as our product. Okay. We will get this as our product. So the next question they have asked, what will be the suitable reagent for the following conversion? So they have given this alpha beta unsaturated compound and undergoes a epoxidation. Whenever this alpha beta unsaturated double bond, there will be a H2A2, and so these two are already cut. These two are already cut. Now to complete just for examination, just to confuse you, they have given H2A2 NaOH and H2A2 acetic acid. So if you just get confused, like if you remember the H2A2 but you don't know the combining reagent along with that, and you take this one, so this will be the wrong one. For epoxidation you need H2O2 NaOH. You need H2O2 NaOH, not H2O2 acetic acid, not this one, because in case of H2O2 acetic acid it will give OH plus, but whereas in this case you need a peroxide anion. You need a peroxide anion for the reaction. So for this one it is always H2A2 NaOH. You have to know that second part of the reaction, second part of the reagent also. You need combination of H2A2 NaOH, not H2A2 acetic acid. This is just to confuse you. They have given these two options. Okay. So whenever there is alpha beta unsaturated double bond, what reagent we will choose? We will choose H2O2 NaOH, not MCPB. MCPB is for electron rich double bond. Now this next question. I think this question I repeated just. I have already discussed this one. So next topic is ozonolysis. Next topic is ozonolysis. So in the first slide I have already, there are different type of oxidation processes there. In the last class I have discussed. I don't have the slides to read. If you are having a double bond, there are three type of oxidation can be possible. I have discussed in the last class. Three type of oxidation is possible. One is dihydroxylation. Another is epoxidation. And the last one is just cleavage of the double bond. Just cleavage of the double bond. Just cleavage of the double bond. Okay, so there are three types of oxidation. So the first one we have discussed already in the last class. Second one also we discussed in the last class, and we have today we'll solve some questions from that to give a clear idea. So the last one is the ozonolysis. So what is ozonolysis? It starts with 1,3-dipolar cycloaddition reaction. So if you have a question like what is 1,3-dipolar cycloaddition reaction, we will discuss this in the next upcoming classes when we will discuss about pericyclic reaction. Then in that cases we will try to discuss about this 1,3-dipolar cycloaddition. So for now just get an idea, but eventually becomes a method for cleaving of pi bonds. They end up giving 2 carbonyl groups, and the reagent is ozone. So if you have this double bond and add this ozone and this Me2S, what will happen? Just this double bond will cleave and will get this oxidized product. How will get this ozone? So in laboratory, if you try to generate ozone, there is a machine like this type of box is there. This is a ozonalyzer machine. This type of box is there. So there is a pipe here, connector here, and there is a connector here. In this connection, there is a oxygen cylinder. If you are taking oxygen cylinder, you are connecting this with the oxygen cylinder. This is the oxygen cylinder. What will happen? This oxygen will go from there into this machine. This machine is a ozonalyzer machine. What will happen? This will combine 3 O2 is equal to 2 O3. 2 molecule of ozone. 3 O2 is equal to 2 molecule of ozone. So that it will take oxygen, and in this machine it will generate ozone, and it will, if you connect a pipe here also, it will give ozone from here. It will generate ozone from here. So 3 molecule of oxygen will enter, and then in the machine it will give 2 molecule of ozone. So this ozone, if you are adding this ozone into this, it will be a gas. This is a gas. So if you just enter this pipe into your reaction vessel, and where the substrate is already there, then it will undergo this cleavage and form this carbonyl compound. So there are 2 types of, now to quench this ozone, suppose this is, now this reaction has happened, now there is some excess ozone. If the excess ozone is still there, it will keep reacting with this carbonyl compound also. To quench this one, we are adding Me2S. What will happen? This Me2S will attack to this ozone and it will quench this. And it will quench. And it will quench this. Okay. So this can be, this ozonolysis can be oxidation and oxidizing ozonolysis and reducing ozonolysis also. Like if you are not, instead of this Me2S quenching reagent, if you are adding H2O2 into it, like peroxide into it, what will happen? Whatever aldehyde is there, if there is any aldehyde, those aldehyde will undergo the oxidation and will give acid in the reaction medium. And instead of H2O2, if you are adding NaBH4, these 2 aldehyde will reduce and give alcohol in the medium. But if you are taking this one, if you are taking this double one, what will happen? It will give this. Whatever reagent you add after ozone, that doesn't matter. It will always give these 2 ketone. It doesn't matter whatever reagent you are giving. After ozone, if you give Me2S or H2A2 or NaBH4, anything. Or if you add NaBH4, that will be a different, but if you add H2A2, in both of the cases this ketone will be obtained, because there is no such hydrogen is there to undergo the oxidation further. Okay, there is no such hydrogen is there to undergo the oxidation further. But if you add NaBH4, what will happen? These two will be reduced to secondary alcohol. Understood? So if we look into the mechanism, first this ozone, one molecule of ozone is coming here and it undergoes this 1,3 dipolar cycloaddition reaction. This comes here and this goes here and form this type of oxidant intermediate. After that, this undergoes a cleavage. This comes here and this carbon-carbon bond undergoes a cleavage and form one molecule of ketone and another molecule of this carbonyl oxide. So one molecule of ketone is already generated. So this part will again combine with this one. This part will again combine with this one and form this intermediate. This part is coming here and this oxygen center is attacking here. So it's forming this intermediate. After that, when you are adding Me2S, this is attacking here, this moves here, and we are generating two molecules of carbonyl compound. So usually instead of DMSO, we can use PPS3 also as a electron donating agent. Now instead of this one, if you use H2A2 will give OH. That will also react in the similar way and do the reaction, but further this OOH will oxidize our aldehyde to acid. This OOH will oxidize aldehyde to acid. Okay. Just see the mechanism once. So, based on this ozonolysis, there are some questions that came in previous year. So they have given this substrate and undergoes ozonolysis. After that, they added NaOH and palladium charcoal. What will be the product in this reaction? So if you are adding ozone, there is only one double bond, so it will undergo the cleavage of this double bond. So we will get one carbon in here. Now if you are adding NaOH, there are two carbonyl compound and NaOH is added. What type of reaction you can think of? Aldol condensation. What type of reaction you can think of? Aldol condensation. You know about aldol condensation. Whenever there is alpha hydrogen, that will be picked up by NaOH and will attack to another molecule of carbonyl compound. So as there is alpha hydrogen here, so there are three types of alpha hydrogen. There is one is here, one is here, one is here, one is here. Okay. So if you take this alpha hydrogen, it will attack to this carbonyl compound. So how many member ring will form? It will form 4 member ring. From the options you can see there is no such formation of 4 member ring. If you take this proton, and then attack this center, how many member of ring will form? It will form a 4 member ring. That will not be also okay. If you take a proton from here and attack here, how many members it will form? 1, 2, 3, 4, 5, 6. This is possible, and if you take from here and attack to this carbonyl, that is also possible. So let's try both of them and let's see which one gives our product. We are taking proton from this position. Possibility is this one. Now if you take proton from this place and attacking to this carbonyl, there is already a methyl group is already there. So there will be only formation of this. Whereas this part is reacting with this part. Okay, so there will be double bond here, and beside this double bond there is a ketone. There is a methyl here. There is a double methyl here also, and just beside that there is a OH. Now, if we add palladium charcoal, it will undergoes aromatization. So this proton comes here. There is a proton here. That comes, and this ring also undergoes aromatization and will give palladium charcoal will undergoes aromatization, like what it will take whatever hydrogen is possible to take and to give aromaticity. So it will take all the hydrogens. So this will be our product. This is the option B. So this will be our product. Okay. Let's go to the next question. So this one I will just give as a homework, because the first step is simple batch reduction. If you some of you know about batch reduction, the first step is batch reduction. I don't know, some of you may know about this batch reduction, so just try it at home. Next class I will discuss about this batch reduction, so then we'll solve this one. Okay, so just take it as a homework and try to solve it by yourself. We will solve it together in the next class. Okay, so let's solve this one. Number of carbonyl group present in the final product of the following reaction sequence. So how many carbonyl center will be there in this product for after the reaction? So as it is O3 and H2O2, so obviously it will be a ozonolysis, and H2O2 is given, so it will be a oxidation ozonolysis. That is, after the cleavage of the double bond, this reaction will not stop. Whatever aldehyde is generated, that will be oxidized to acid. If there is ketone, there is no such case, but if any aldehyde is generated, that will be automatically oxidized to acid. Then only one double bond is there, so we are cleaving that one. So this is the aldehyde, so it will be automatically oxidized to acid, because the quenching reagent is peroxide, not Me2S. The rest of the compound will be same. That part will be also acid, because as this is aldehyde, so it will be automatically oxidized to acid. The rest of the part will be unaffected by this ozonolysis. After that, in the next step, what they have added, they have added H3O plus and heating. So whatever H3O, if H3O plus is given and heating, so whatever ester group, ester will be hydrolyzed. There is a anhydrate, so that will be hydrolyzed. So if it's taking this H plus, then on a molecule of water molecule will come here, and it will open up. It will open up and it will give us it will be acid. Anhydride will be open up, so it will form two acid group. Here also there are two acid group. So now they have asked how many carbonyl groups will be there. So what are we call carbonyl groups? Only the aldehyde and ketones are called the carbonyl groups. So we will just consider the aldehyde and ketone, not the acid ones. Acid ones are not considered as a carbonyl group. So this is 1, 2, 3, 4. So the number of carbonyl group will be 4. So from GATE no question, you know, you just have to write 4. If you write anything rather than 4, the question will be incorrect. So the correct answer will be 4, and no options are given for this NAT type of questions. Okay. So this is another type of question for epoxidation, for asymmetric epoxidation. For asymmetric epoxidation, I am giving this as a, not as a homework. I will solve this just for now. We are just keeping it hold because today we will not discuss about the asymmetric version. In the next class we will try to discuss about this asymmetric epoxidation, while we will try to solve this one, and I will also show you a trick to solve this type of question, because during your examination sometimes it's very hard to predict the stereochemistry of your product. So there is a very short trick where just by seeing the substrate and your reagents you can predict, okay, the epoxidation will be above the plane or below the plane. So we will discuss about the trick also. We will discuss about the mechanism as well as the trick to remember how we can determine if the product will be above the plane or below the plane, because sometimes we get confused. Okay, for this substrate is above the plane, for this substrate it will be below the plane, so how we can get that? So trick we will discuss also. So this much for today's class. Thank you everyone. So this is the overview of this class. Today we will discuss about the metal-free reagent oxidation reagents, this DMSO, DCC, DMSO electrophiles, Swan oxidation, Dismutin oxidation, tempo. Then we solve some previous year questions. Then we discuss about ozonolysis and some previous year question based on that also. Then we'll solve the asymmetric version of the epoxidation in the next class. So thank you everyone. Have a nice day.